Okay. So my apologies to give this talk. No, I should probably have it done later in the year when there are maybe when there is less activity. But since I only have a limited stay, somehow this seemed to be the only time. So what I want to discuss are some results and also problems that have to do with the values and the spacings of the values of diagonal forms, with special emphasis on quantitative aspects. So definitely there has been there have been a number of very spectacular results about the distribution of say quadratic forms, the values of quadratic forms on the integers obtained by ergodic methods, and actually results that are deterministic in the sense that they apply to individual forms. The only drawback is that somehow these results, say quantitatively, they are usually phrased in non-quantitative forms, in a qualitative version, and quantitatively it's not really sure what one can extract from these methods. But anyway, it doesn't look like one really gets the expected quantitative results in some sense. So this is something I want to address in this talk a little bit more using other methods. So these ergodic techniques is not something which, to say the least, I have real expertise in. On the other hand, there are other techniques, say, which are slightly closer to my heart, let's put it like that, which I master better, and also have the potential of leading to a certain explicitness in terms of quality of the bounds. The only drawback is that, well, in some sense, they are considerably less powerful than ergodic techniques in the sense that these analytic number theory arguments, which I will show you, they only give you something in the generic setting, generic in the measure category. So I think still their interest is that they kind of give an indication what should be true, perhaps also in the Diophantine, in the Diophantine context, beyond the generic results. But this is something right now we don't have a hold on, and it looks like there is a big gap somehow between, say, what one can do with this ergodic method, say, for individual forms, even in the best possible case in terms of the best possible arithmetic assumptions, and what one can prove, say, in the generic measure generic thing, and the measure generic setting. Now, although these results are, well, only stated, say, in fact, for families of quadratic forms, and that you could expect, well, if you go in the measure sense, things should be easier in some sense. Turns out that there is still, it's still not completely obvious, and there is some idea there which is going to underlie the different results. And once you assimilate this idea, then basically the way things run, it's, I would say, rather elementary standard analytic number theory techniques. But still, in some cases, you really get the best possible results, and it links with some other problems. So let me start with reviewing what will be on the table, roughly speaking. So first recall a remarkable theorem of Margulis, Dani Margulis, which is a purely qualitative theorem, but again is a result for specific quadratic forms. So we are considering an indefinite ternary quadratic form, which is not proportional to a rational quadratic form, so I will call it an irrational quadratic form. And then you evaluate this quadratic form at the integers, say for v in Z3. So it's, for instance, x squared plus y squared minus a z squared, where a is a irrational number. You evaluate that at Z3. On Z3 over the primitive vectors, and you get something which is dense in the real line. So one can, of course, start asking, what does it mean quantitatively? In other words, if I want to approximate a real number by a QV, basically, how large do you have to choose this V? So this problem, well, even after the work of Daniel Margulis, is definitely a non-trivial one, and there is a remarkable follow-up on that, which is, roughly speaking, based on effective versions of Ratner's theorem, which is due to Elon and Margulis, and somehow makes this a bit more precise. So we are again starting from a Q, which is an indefinite ternary quadratic form. No, we're not making any rationality assumptions at that stage, because that would be part of the statement, say the quantitative statement. So we normalize Q to have determinant 1, and then we take any epsilon. So there is a dichotomy, and this dichotomy basically tells you that either your quadratic form is proportional to an integral quadratic form, which determinant is not too large, or you have this, so that is in some sense quantizing the fact that the quadratic form looks like a rational one, or you have this other property of approximation, namely that that if you take say some real number and we restrict it to an interval, I'm not so worried about where you choose that number xi. We could even choose xi equals 0, for instance. But what you see is that if you want to do the approximation, well, I mean, if you're allowing evaluation on vectors v, which are as large as, say, t or capital of t, the approximation you have is actually very poor. It's only like a power over 1 over the logarithm. So this is what I was referring to before. You want to achieve a certain approximation. How large you have to choose a vector v? Well, basically, it's an exponential dependence. So likely this is not really the end of the story.
This is not what's expected, or?
No. I will show you from the generic point of view, in some sense, what one could expect.
Also, I don't know what you mean by what do you mean by primitive? Being primitive.
Just the coordinates are the greatest common divisor is equal to 1. I'm trying to get my pointer, but somehow the pointer seems to be.
And the pointer sometimes. The stick is much better.
2 sticks. Yeah. Okay. No. So actually, that's a good question. What can one expect? So let's try to be more specific. So basically, you're considering vectors x in Z3 with size of x bounded by n, and then you want, with such vectors, say evaluating your quadratic form on such vectors, find the best possible approximation of a, say, a real number xi, where we take C in a certain range, say, let's say C is bounded by a function A of n. Don't worry too much about the function A of n. I care more about the function delta of n for the time being. Right? So you want an approximation up to delta n of any real number C which is bounded by A of n, and that by evaluating your quadratic form at a point x where the size of x is bounded by n. So the question is, how do these functions A of n and delta n depend on n? So from the previous results, what we're getting is a certain dependence which is logarithmic, because, well, basically this n would be the t at the power c, and then the delta n which we got there was only like a logarithm. So if you retranslate that, what you see is that this delta n is only logarithmically behaved in n. So now the question is, what can you expect? So let us consider the generic setting where we would, well, in fact, generic A will be very modest. A will only need one parameter. So we are considering a one parameter family of diagonal forms of signature 2, 1, x1 square plus alpha 2 x2 square minus alpha 3 x3 square, where I will say keep the alpha 2 fixed and let the alpha 3 vary. So we have a one parameter family. And then what it turns out is that we have the following thing. Under assuming, so what happens is that, so alpha 2 is fixed. What happens is that for almost all alpha 3, we have the following statement. If you assume the Lindelöf hypothesis, then we have that if I just take c equals 0, the minimum of qx for x in Z3 and x between 0 and n is going to be basically bounded by 1 over n, say n minus 1 plus epsilon. Note that this statement is true for, is going to be true for all n, okay? In terms of these quantities a, n, and delta n, we get that statement here. So what you see here is definitely a much better behavior than what you got from the ergodic technique, say, for individual forms, where instead of the 1 over n, you got, in fact, 1 over log n at some power.
And most means in measure theory or measure theoretical?
For me, most is always in the measure sense. Now, if you don't have the Lindelöf hypothesis, then you can prove something else which is slightly weaker and can be improved. Well, I must say I will say a word about that, but I haven't really worked extremely hard to get the best possible out of that, because somehow it didn't look possible to really match what you got from the Lindelöf hypothesis without making further assumptions. Yeah.
Could you expect to get the same result for all points but a finite set? For all parameters alpha 3 but a finite set?
Well, you could start wondering whether, or even say more modest. Well, in any case, you would have to assume that. But you could start wondering once you have that, maybe proving something outside a set of lower Hausdorff of smaller Hausdorff dimensions and kind of things like that. So here I'm excluding a whole set of measure 0. Maybe it's enough to exclude a set of lower dimensional of smaller dimensions. Something this I haven't really looked at. It doesn't fit. It doesn't fit. No, it's fine. It doesn't fit the technique very well. But say the first step was at least to understand what happens in the measure sense. And like I said, it's not. I mean, it's once you know how to handle it, it's not very difficult. But you need to have the right idea how to do that, and I will come back to that. So, say possibly a statement like that could be true in the Diophantine setting also, but say the best possible Diophantine setting, but we don't know.
I understand these problems are
most difficult in the ternary case? I mean, if I go to a higher order, if I go to a higher.
Yeah, well, that has a whole history, of course. 3 is say the worst possible. 2 is false. 3 is the worst possible because somehow you have less. That then becomes easier. And that has a whole history, Davenport and all these guys, 5, etc. I mean, this is the whole story of this Oppenheim problem. So if you have more variables, then you have all kinds of other techniques available. Yeah. Which works for individual forms. They don't need to have any genericity. So say if you have 5, they are of the strength of what Margulis done. He did, and even quantitative. And quantitative because you have enough variables. Yeah. That again comes from analytic technique. Well, I mean, ergodic theory is also an analytic technique, but when I say analytic technique, I really mean analytic number theory type technique, circle method. So, of course, to answer that question, this is the best possible. Intuitively, and in fact, if you think about it, you realize that this is indeed the best possible. Why is that? Because I have 3 variables. We're going up to n. The range of qx when x is bounded by n is n squared. So 1 over n is what you expect. In fact, you can prove that this up to the upsilon that this is the best you can achieve. Now, if instead of having a 1-parameter family, I have a 2-parameter family, so I would let alpha 2 and alpha 3 be both parameters, then I wouldn't need Lindelof. That's a small comment. And what I should also say is that quite recently.
I would say that taking 1 parameter wasn't modest. It was the opposite of modest. Modest would be to take.
No. What I'm saying is that the amount of extra measure freedom I need is modest because I only play on 1 parameter. So there are some recent papers of Gauche and Kellner who prove such results using different techniques. But they are very recent, they came after that actually. They are results for generic elements in the full space of indefinite ternary quadratic forms. So we are not talking just about diagonal ones. Diagonal has less parameters, of course. If you are in the full space, then you get what, a 5-parameter family or something like that. So you're better off.
But that's not optimal.
What's that?
Gauche and Kellner don't get the optimal.
No, they have a second paper. They have a second paper when apparently they get something which is closer to optimal.
Okay.
Now the next thing is the problem of eigenvalue spacings of flat tori, and basically I'm getting closer to what initially triggered these investigations. So let's say a word about that. So there is apparently a conjecture which tells you that if you have a generic integrable quantum Hamiltonian system, then the local statistics of the eigenvalues coincide with those of random numbers generated by Poisson process. So somehow the simplest case to test such a conjecture would be to look at a flat torus, so take a 2D flat torus. And so what we are having is a lattice gamma, and then we have R2 mod gamma, which gets you 2-dimensional flat torus. And you can look at the eigenvalues, which are given by an explicit formula, 4 pi square of the norm of V, where V runs in a dual lattice. In other words, what you're getting there are the numbers 4 pi square of n1 v1 plus n2 v2, where v1 v2 is a basis for the dual lattice. And so you have a quadratic form. In n1 and 2. So at that stage we only have 2 variables, which are n1 and n2. Well, that quadratic form, so there is no mystery about these eigenvalues. That quadratic form evaluated at integer n1 and 2, that gives you all the eigenvalues. And we have Weyl's law, and well, beyond Weyer's law, the next thing you would worry about if you study the statistics, say the local statistics, so a classical thing to consider is a so-called pair correlation. So we're looking at local spacings. And well, the proper quantity to introduce is the following. We are taking some large t, and then we are looking at the pairs gk of eigenvalues, distinct eigenvalues, with lambda j, lambda k bounded by t, and the difference, say, in an interval ab, where, well, a, b, say, are given and fixed, but we will also be interested, well, I mean, depending on the setting, but in that case, we will also be interested of having the gap, the size of that interval, becoming small with n, in some sense. So in any case, according to Barry table, if we consider these eigenvalues as random, then it is clear what happens in the limit for t going to infinity with the normalization I made. We expect that RABT behaves like b minus a up to a factor which is the square of this constant Cm in the Weil law. Why? Well, I mean, roughly speaking, what happens is that if we're going up to t, so we are putting a bound on that by t, so the number of pairs n1 and 2 is going to be of the order of t, right? So we get eigenvalues, number of eigenvalues is going to be of the order of t, and so what we expecting is an average spacing which is order 1. That is specific for the two-dimensional case. If you are in a three-dimensional case, it's a different game. We'll come back to that. So in any case, this proportionality with b minus a is natural, so that is the natural window. B minus a, so the natural window, say, at least at first investigation would be order 1. As we will see in certain problems, we'd like to let b minus a go to 0 with t, and even in the extreme case when we're looking at minimal spacing. So we'll come back on that. So in any case, the first time where in, say, some setting, this Barry-Tabor conjecture was verified is a paper 96 by Peter, which is a measure. It's again a measure generic setting, namely that data asymptotic holds for a set of full measure in the space of all tori. So we are not talking there about just rectangular billiards, talking about all billiards. That gets you, in fact, two-parameter family. And this problem is exactly about the spacings. So you have quadratic forms in two variables, but when you're looking at spacings, lambda j minus lambda k, eventually you end up with a quadratic form in 4 variables, which is of signature 2, 2, of course. Now, what should be said is that apparently it is not obvious how to prove a result of that kind when instead of considering the space of all tori, you just stick with the rectangular case. So instead of looking at all lattices, you're only considering a specific class of lattices. You have less parameters to average. If you are consider the setting of general flat torus, you have 2 parameters. If you're looking at rectangular billiards, you only have 1 parameter, and somehow making this argument run on 1 parameter did not seem obvious. So this somehow was a starting point for me, and you will see that, say for us, you will see that in a moment, is that we were kind of trying to look for an say a variant of that results of Peter, where instead of taking all the tori, you stick with the rectangular setting. Now, in if you're looking for deterministic results, in particular in the class of rectangular billiards, what is applicable is another remarkable theorem, which is obtained by ergodic techniques. That is 2005, Eskin, Margulis, Moses, which tells you that statement holds for any billiard, say, in particular rectangular billiards, provided you have some Diophantine assumptions. So in the setting of rectangular billiards, it would be okay if we assume that alpha is Diophantine, and in fact Diophantine in a very weak sense. Any kind of weak sense suffices. The only trouble of that is that for what we wanted to do, it was rather useless, because it doesn't give any kind of bound, any kind of information how fast you could, let's say, b minus a go to 0 and t going to infinity. And so we questioned, this was earlier this year, we questioned some people about that, and more who have more the expertise in that, and they...
Is this kind of like a density of states?
Yes, yes.
And then you want something final.
Well, for instance, that would, for instance, exclude that you have an atom. It would exclude... Tom, it would exclude that you have an atom at 0.
Yeah.
But then you want to see how much concentration you could have there.
Pair correlation already controls some, as he's saying, consecutive state. That's much harder.
So their verdict was that at the best, although this was nowhere written, maybe you could get some kind of, again, a 1 over log t or something like that. And this was not good for what we wanted to do. So what was really the initial motivation? Well, the initial motivation was to understand small gaps. So what I'm rewriting there is this Weil law. And so what we can look for is the minimal gap of eigenvalues, say up to n, and then we like to say how large it is. And well, basically, if we believe Poisson statistics, it should be like 1 over n. The trouble is that if we're trying to apply something like Eskin, Margulis, Moses, we have no way of taking b minus a as small as 1 over t or something like that. That is the trouble. So we were looking for something else, and the something else, of course, was Peter's argument, because Peter's argument was a conventional analytical treatment. But the trouble is that it seemed to require more parameters. This is what I was saying in the beginning, that of course in the measure category things are easier, but they are still not completely trivial. So yeah, well, about this Poisson statistics, this is something I'm not an expert in, but this 1 over n gap is of course specific to this Poisson setting. If you're looking at other ensembles, you get different results, because there is a certain repulsion. I don't know whether this is...
You misspelled the one author's name. He's Bloma, not Bluma. No.
Yeah, you're right. Okay. Never blame your secretary for such things. So in other ensembles, there is a certain repulsion going on. So the 1 over n behavior is specific for the Poisson behavior. And well, what it turns out...
I'm sorry, what is this delta? I mean, maybe...
Minimum spacing.
Yeah, maybe
The small, well, it's just a smaller spacing of 2 eigenvalues up to n.
Yeah, can I just go back?
Right. Okay.
I
Okay.
didn't
Okay. Okay.
absorb that last definition.
So we are looking at delta. So the alpha.
Yeah, what's the alpha here? Oh, I see.
The alpha is from the billiard. The alpha is the ratio between the sides of the billiard.
I mean, the ultimate conjecture here, if you believe it, is alpha is
Yeah. By the way, we really have no hold on the statistics of the lambda a plus 1 minus lambda I, right? Let's put it like that. We have the pair correlation. I mean, there's no method which gives you that. But still, we can talk about the minimal spacing because we're just the same thing. Yeah? So what did we prove? This is with Blomer, with 1O, Radziwill, and Rudnick. So what we proved is that indeed, generically, in the measured generic sense, with respect to alpha, we have a bound which is about the right bound. Now, conversely, there is a lower bound. Well, at least what we can show is that for most alpha, infinitely often, this Poisson statistics is kind of slightly violated, but not seriously, just by some power of a logarithm or something, but which may still be worth to observe, although presumably people in this area will absolutely not be worried about a discrepancy which is only of a logarithmic size, but just to point out that there is still something there which is not just Poisson. So the next thing, since we're talking about two-dimensional billiards, is what happens for 3D billiards. Now, luckily for me, in some sense, in the 3D case, the ergodic methods, they absolutely don't work anymore for some reason, which will be clear in a moment. If you have, say, looking at this time a ternary quadratic form, which would give me the eigenvalues evaluated at the integers, x1 square plus alpha x2 square plus beta x3 square, say, evaluated, x1, x2, x3, say, bounded by n. So what we're getting there are n cube numbers, which are bounded by n square. So even if we're just talking about typical spacing, in the sense of what was looked at, say, by Eskin, Margulis, and Moses, well, we have a b minus a there, which is not anymore order 1, but it's order 1 over n. And apparently, this is a serious issue to make such an ergodic approach work, because there is a dependence there of that gap in terms of the range of the variables.
Alon, is there a translation of that to some quantitative distribution in the space of lattices?
Yeah, I was trying to think. I don't. Off the top of my head, I don't see.
Well, I'll be honest. Zeev Rudnick is the one who pointed this out to me. Apparently, no hope to do it.
I'm just asking what it converts itself to dynamically. Yeah. It doesn't convert itself to Oppenheim, that's for sure.
Not that I'm aware of. So here we are not talking about the smaller spacing. We are just talking about the generic spacing. So that, in some sense, is the easiest question you could wonder about the statistics, say, of the eigenvalues for a rectangular billiard. So what we do, we introduce again R, A, B, T. We take Qm, Qn bounded by T, and Qm minus Qn in an interval A, B, keeping in mind that this time B minus A should be of the order of 1 over n or smaller to make it interesting. And then we normalize by, so we have n to the third, which corresponds to T at the power minus 3 halves.
But this answers Tom's question. You have more variables here, but you ask now because you unfold.
Yeah, you have more variables, but the window becomes smaller also. So I mean, the advantage you get from the variables is lost is laid off by the size of the window. So the role of the Cm now is played by the C. Now the C is just what you would get if you forget the integrality. So drop the integrality condition and just take the variables x1, x2, x3 continuous. Right? So that's the result. What they proved is that, so let's say we fix A, B. Let's take them O1 to make it simpler. let's say we have a window here, b minus a, which is bigger than t minus rho, where rho is anything less than 1. So in particular, if I want to recover the 1 over n, that would correspond to rho equals a half. So the result I'm stating there covers, say, the typical spacing we're really interested in. So then what we have is an RABT which behaves like that constant c, t to the power half, which is like n times b minus a. So typically that business here should be order 1. Of course, we can take a little bit smaller with some limitations, and maybe one can do slightly better. But in any case, it captures, say, the analog of the Eskin-Margulis-Moses theorem in the case of a 3D rectangular billiard, at least generically, when we're letting this alpha beta being parameters. Maybe you can do something with only 1, but this in a way it's written for 2. And as far as I know, there is no other technique to handle that in some sense. What I should also point out is that there are results, are older results by Jeffrey van der Kam, who studies the pair correlation, but again for not now for rectangular, but for generic flat tori, using another procedure, but that procedure only works in even dimension. So the trouble there is that you have this 1 over n, this very small spacing. So what you can do to avoid this small spacing is a process of unfolding. So the unfolding is that you would simply take a power. So instead of looking at lambda j, you would look at lambda j square. And then the spacing there would become order 1, say. The only trouble is that this thing only works, say, in even dimension. So you would do that, and then, of course, you have to study the distribution, not of quadratic forms anymore, but higher degree forms. That speaks for itself. As a full set of parameters, then it's restricted to the even dimension. So the next thing, still in line of what van der Kam was studying, is what happens for higher degree. So van der Kamp was looking at the full space of homogeneous forms of degree k in k variables. I'm looking here only at the diagonal ones. So we have f x1 xk, x1 to the k plus alpha 2x2 to the k plus alpha k xk to the k. K minus 1 parameters, alpha 2, alpha k. So we have n variables which go up to n. So a range of f which is going to be like n to the k. So we have n to the k values within an interval, say, of size n to the k. So what we are expecting is that on average these spacings should be order 1. So that we are looking for now in terms of pair correlation is a window which is order 1, although we can do slightly better. And again, say, in a measure sense, what one can show is this Poisson statistics. With
there is no ergodic theory that even, right?
Well, I'm not an expert, but
you don't. The beauty of quadratic forms is
quadratic forms are special.
You got a group action.
Yes, yes. It's not clear how you do that by moving a lattice around in that case. So you can even do slightly more. You can let your b minus a even go to 0. See what happens for smaller windows within a certain margin, say. So at least there is some rho positive where it holds. Just to point out that the results, they come with a power gain. So you get this asymptotic even letting b minus a go to 0 with capital T, provided it doesn't go too fast. So
and the row that you have there is
or some positive number.
it related to the k or the degree?
Presumably, it didn't give too much attention to make it, say, best possible in some sense. The first challenge was to cover the typical spacing, which is order 1, And then next you see what is the limitation of your argument, and you realize that actually you can have a spacing which is even a little bit smaller, say, than order 1. You can let it go to 0 with t at a certain rate. So just to point out that what we are having here are not logarithmic restrictions, but they're really power gains. So now what I told you is that these arguments are not very complicated, but still there is some idea behind it, which is recurrent in all these proofs. You see, the natural thing, for instance, if we're looking at the squares, things involving squares, is that you try to attack it with Gauss sums. And that's what we tried for a while, and you kind of seem to turn in circles because you go from the arithmetic to the Gauss sums, then you try to do some analysis, and very quickly end up again with the problem of arithmetic. So you kind of turn into a circle, and so something else had to be found. And somehow the idea is that instead of writing this problem additively, strangely enough, by writing this problem multiplicatively, you get out of the Gauss sums, and instead you're getting Dirichlet polynomials. Now there is something nice about Dirichlet polynomials, is that, so these are, say, a standard partial sum of the zeta function, is that they are small as soon as you take t away from 0. So for instance, if you assume Lindelöf, you would have an almost optimal bound here, square cancellation, which is square root of n. And so the effect of that, and this is what you want to do in all these proofs, is kind of separate when you do Fourier analysis, the contribution of small t and large t. So basically, when you have small t, there's no difference between integers and reals, and you get your Poisson statistics trivially. But then the trouble is to discard the effect of large t. And that can be done exactly using that kind of phenomenon, because for t large, you get very good bounds on these Dirichlet sums. So in some sense, it's, roughly speaking, it allows you to discard the effect of the higher Fourier contribution, which is what also appears in Peter's argument. And somehow here to implement it, there is this little point
so
here.
N approximate cap n means what?
Well, you will see. I will show you an argument. Once you get that idea, then it's an exercise, right? So let me just show you how this works. So for instance, we want to study Oppenheim, x1 square plus x2 square minus alpha x3 square. And let's say we are interested in understanding how well we can approximate 0. So x1 square plus x2 square minus alpha x3 square less than delta, where we like delta to be as small as possible in some sense. Right. So instead of writing this, we're writing that. So we are taking x1, x2, x3 of the order of n. So this is existence. We want to find x1, x2, x3 so that is small. Well, we're going to take x1, x2, x3 of the order of n, and then we see how small we can choose delta. So instead of writing it like that, I write it like that. And instead of writing it like this, we can write it with logs. So at that point, we switch to Fourier analysis, and we are counting x1, x2, x3 that satisfy this inequality, just by rewriting it in terms of Fourier. So what we're getting here is f1t, which would be given by partial sum of the Epstein zeta function, and an f2t, which is the creature I mentioned to you before, which is just a partial sum of the usual Riemann zeta function. And so what we have to evaluate is this creature here, where t here is going to be the reciprocal of that, which is n squared over delta.
This should be log.
What?
You're taking logs.
No, this is correct here.
Okay.
Log 1 plus x is of the order of x. That's what you're using for small x. So there is no log. So we have a t here which is quite large. So we're taking here an integral over t's which is quite large. But the idea is that you can look at small t's where the problem is trivial because there's no distinction anymore between integers and real numbers, and large t's. And then you want to discard the effect of these large t's. So this is done very easily. I'm writing here a square root of n, but I could put anything here. I could put n at the power 1 over 10 or n to the epsilon for 1. But let's do for simplicity, let's take n 1/2. So you have this analytical expression from before, and I'm splitting the integration range in t's which are less than square root of n, and then t which are between square root of n and capital T. Now this first contribution, well, you go back and you see that that corresponds to this here. So instead of having now an approximation which is 1 over t, I have an approximation which is only n minus a half, and where there is absolutely no difference whether I'm taking the x to be integral or not. So that is evaluated right away and accounts for the main contribution in the Poisson statistics. Note that at that point I haven't used anything about alpha. So what happens next is that we have to evaluate the effect of that second term. So now we are doing an average in alpha, and recalling the format, the way this expression appears. The obvious thing to do when you do an average in alpha and you try to see what is happening is to bound the average in alpha by an L2 norm, say, and apply simply Parseval, which brings you back to bounding F1 and F2. So if you do that, what you have to, the, say, average effect of the error term, it's given by this expression, which you split in a maximum of F2t, and then, so what you do is that you put this one outside here. You take the maximum. Note, it's absolutely essential to take t away from 0 here in order to control that. Otherwise, the whole thing wouldn't have a sense. Here, you're controlling, you need to control an L2 norm. It doesn't matter whether t is close to 0 or not. You're taking the full range up to capital T. And we're trying to make bounds on that. So assuming Lindelöf, you get right away an estimate by square root of n on the maximum of F2. And then in terms of, for the second factor there, this average, you just write it out and you get, this is a trivial calculation. You see what it means, and eventually you see that you get a bound here which is of the order of n squared. So your error term in the mean is bounded by that, and it turns out that as long as delta is sufficiently large, this thing is going to be very small compared with the main term, so that you can conclude that for most alphas you're going to have this behavior. And this thing works all the way up to 1 over n. So you can try to avoid Lindelöf and unconditionally get something slightly weaker. So what is, and you can improve that, you can perhaps slightly improve that. So what is involved there, these are standard techniques in number theory which people have developed around so-called large value estimates. Say, try to understand the distribution of the zeros of the zeta function or Dirichlet L function. So there's all technology there that has been developed by many people, Montgomery, Huxley, and so on and so on. And so in particular, there is a technology to say something about the distribution of Dirichlet polynomials. So what I'm using here is a distribution inequality which is due to Jutila. And so you would wonder, okay, why do you consider such a general object, while in fact I was talking about F2t being the sum of n at the power it. It's just that you apply this inequality where your Dirichlet sum is actually the square of F2t. So you get quite arbitrary coefficients because they are involving divisor functions, etc. And like what often happens in this theory, because you are powering, you're taking power somehow to adjust the length of the interval. And so what is happening is that you really get a Dirichlet polynomial of general kind, and you're applying this distributional inequality to S of t, which is obtained as the square of F2t and which is still basically of that form. So this is one thing which is used. The other thing which is used is a bound on Epstein zeta function. So here one has to be a little bit careful. So what I'm using here is something very simple, which is basically the equivalent of Titchmarsh bound for partial sums of the zeta function. So let's assume T is sufficiently large for simplicity. Then we get a bound of that form. If you would have one variable, then the bound would be n at the power 2 times t at the power 1 over 6, which you recognize quite easily if you're a little bit familiar with this theory. These estimates, in fact, come from van der Korput's third derivative estimate, which is saying, can be rephrased by saying that 1 over 6 2/3 is an exponent pair. So for the usual one-dimensional sums, it is a standard exponent pair. Now, what it turns out is that 1 over 6 2/3 is also a two-dimensional exponent pair. Now, what does it mean, exponent pair? Well, you see, what I have here is a derivative. I have to put that in the exponent. So the derivative would be basically like t over n. So the derivative gets the weight 1 over 6. I have to square because it's two-dimensional. The length of the interval is capital N. So capital N gets the power 2/3, but I have to square because it's two-dimensional. Just to make one small comment there, it's not, at least it's not known, that if you have an exponent pair in one dimension, you automatically get it as an exponent pair in two dimensions. So there are certain non-trivial issues there which are not completely clarified. But for 1 6 2/3, it is okay. And if you don't know about exponent pairs and you know the proof in the one-dimensional case, then you can, in fact, reproduce also that proof in that situation, at least in the two-dimensional case. In fact, it was done by Blomer. I think I spelled his name correctly here. In his argument, and this is completely general bound, is that you get a bound for the Epstein zeta function on the critical line, which is like t to the power 1/3, which, like I said, is the equivalent of what Titchmarsh did. What's that? Yeah. What? Yeah. Right.
I mean, Baal never, Baal only estimated on the line 1. He introduced the method at the end.
Well, he thought he could do Lindelöf at some point also. But yeah, we shouldn't stress this too much. So in any case, it's conceivable that there it should be an t to the epsilon. This is for two variables. If you have more variables, then there is a discrepancy, and then you have to distinguish between rational Epstein zeta function, non-rational, etc. And there are certain things happen, but this is beyond. So when I said, well, you can improve, for instance, you can improve that. I mean, there's no question about that. Nobody has done it, and I don't think it's so terribly exciting. Once I was discussing with Blomer, okay, I can improve your bounds, etc., but he also made it clear that maybe there is, to get another saving of 1 over 10,000 there. If you want to do that, then you better work in the one-dimensional case in some sense. Now, let's say something about the small gaps in the spectrum of the rectangular billiards. And, well, amazingly, in this situation, what I managed to do is avoid, or what we managed to do is avoid the use of Lindelöf by some trick. So now we have a quadratic form of signature 2, 2, so 4 variables, and we have to, so instead of want to study the minimum of that, like to show that the minimum is going to be if I take the variables ni bounded by m, that we can achieve something like 1 over m square. What makes sense there somehow is to write n1 square minus n2 square and n3 square minus n4 square as a product. We just make a change of variables. So we're really looking at the minimum of n1 and 2 minus alpha n3 and 4, where ni's are bounded by m. And so there is a question, is it true that for all alpha, so what you would expect here is that this minimum could be like 1 over m square, or close to that. This problem is open, and in fact, at the end of the lecture, which is going to be very soon, I will show you a problem which is even much, much more modest and which we don't know to solve. So anyway, in that paper with Blomer, Radziwiłł, and Rudnik, this was shown in certain cases. In particular, it was shown for quadratic irrationals. We don't know for cubic irrationals. And it was also shown generically. So what I want to say something about is a generic setting. So we have again this question. So somehow here it begs to be handled multiplicatively, right? So less than delta, so we divide, we rewrite it with logs, and we can rewrite it then with Fourier, where there is one function that's going to appear, which is a partial sum of the zeta function. So analytically, this is what we have to control. We can again split in the low range, which is handled trivially, because there it's like just dealing with reals. The integrality doesn't play any role. And then the rest of it, the larger t's. I'd like to show that this acts like an error term. So now we are doing an average in alpha, use Parseval, and we are ending up with an 8th power of a partial sum of the zeta function. Of course, if you have Lindelöf, you control the 8th power by the square, and you get t1 plus epsilon n to the 4th, and then when you see what is needed, you get indeed that it's going to be okay, meaning that the main term controls the error term, provided delta is bigger than 1 over m squared. On the other hand, in that case, there is a trick. Well, we only care about small spacings. We don't really care about the statistics so much. So we have the right to choose the ni's, the variables, in a certain special way. And the way we do it is that we write ni as a product of two integers. One is small, so ni double prime is m at the power sigma, where sigma is a small number. And then the other one is going to be m at the power 1 minus sigma. So why is this interesting? Well, you'll see right away. So instead of that expression, instead of having, not that expression, instead of that expression now, I'm going to have two factors, f and g, coming from the ni prime and the ni double prime. So I'm getting this, and then you apply again Parseval, so you're getting that. And then you do same thing. What I'm getting here, so what I'm going to do, not same thing, no, what I'm doing is the following. I'm going to take the maximum of this expression, and then the mean, just taking the 8th power of ft, integrating in t, 8th power which I'm writing as a square of the 4th power. So the 4th power of ft is going to be a Dirichlet polynomial, which turns out to have the appropriate length in this calculation. This is very close to the whole technology that, say, somebody like Huxley introduced, for instance, which is basically the bracket the bracket technology. Depending on the ranges of m, you have to choose the appropriate power. So somehow the idea of doing this splitting is to get the length of f the right size compared with capital T. Because what I'm going to have here, this is a standard estimate. It's the basic estimate, say, in this theory of large value distributions. The contribution of that here is going to be T, which is the length of the interval, m at the power 4 1 minus sigma, which is the size of the support of ft to the 4th. So ft is m1 minus sigma, take the 4th power, you get m4 1 minus sigma, times the L2 norm square, which is m4 1 minus sigma. So the role of this sigma is to get these two terms, for instance, comparable. So that this, before I would have n to the 4th, and n to the 4th is too large. So what I'm doing is bringing this down by the sigma. And then the point is that although g is a very short sum, still I have non-trivial bounds on that, which came from any technique you want, because I didn't try to be very quantitative, but it's not necessary here. So instead of the obvious bound, which would be m at the power 8 sigma, so the bound on gt is m at the power sigma, the 8th power is m at the power 8 sigma, I'm getting a little better. I get some saving here of tau. And then what you can do, again, is conclude that this error term is going to be small, provided you choose delta sufficiently large, and delta has to be larger than m minus 2 plus 4 sigma, where sigma is this parameter, extra parameter introduced before, but sigma can be chosen arbitrarily small, fixed, so I still get basically m minus 2. I guess I have little time, right? So I have 2 minutes. About the violation of Poisson statistics, what I was saying, that's on the other side, is that typically you will have infinitely often that this minimal spacing is bigger than 1 over n, in fact by a logarithm. This has to do with a deep result which is due to Kevin Ford and in fact solved the problem of Erdős at the time, which is a quite elementary issue that we are looking at all the integers which are obtained by taking, so positive integers obtained as product of two integers bounded by square root of n. So we're getting here a family of integers which is bounded by capital N. So you can ask yourself, this is the multiplication, right? How many of these integers you're getting?
This is the fact that they don't cover.
Yes.
Upper bound. It's a lot.
Well, Erdős conjectured that the number is little o of n, and he proved that also. And then the question is, what is really the right result? So this result is non-trivial and was obtained by Ford, it appears in, right? It appears in a paper published in Journal some time ago. And so there is a certain constant C.
1 minus log E.
Yeah, and this is the correct answer. So it shows you deviation of these expected Poisson statistics. I was going to discuss homogeneous diagonal forms, which runs very much the same way, but maybe I will not do that since there is a limit of time. On the other hand, what I want to do is just bring to your attention a problem which is much easier. Remember that I was asking you, that I was putting forward the question whether it is true. Let me get back a little bit. So the question is, when you're looking at n1, n2 minus alpha, n3, n4 for ni less than m, the minimum, what is the minimum of that? So you can do the following. Let's just, instead of taking n1 and 2, let's just write any integer there, so that in fact we are wondering, we are asking what would be the minimum norm instead of distance to the nearest integer of alpha n3 and 4 when the ni n3 and 4 are less than m. So at least you like to say that this is like 1 over m square, or 1 m2 minus epsilon. The obvious bound is that
It's just trying to mimic Dirichlet's bound with the condition that both devices.
yeah, that you take them as a product of things. Okay, so like to get 1 over m square, the obvious bound would be something like 1 over m. Now, strangely enough, we don't know anything better than the obvious bound. So this is the question I wanted to put here at the end, is whether it is true that for all real alpha this property holds. So this is a bit a problem in the flavor of the Littlewood. In some sense, it's even more elementary than Littlewood, because in Littlewood you have two, I have alpha and beta. Here I only have one number, alpha. So is it true that if you're taking the limit of the norm of m and alpha multiplied with the maximum of m and n, this thing is always going to be 0. So it's not that we can't get the 1 over m square, we can't even beat the 1 over m. And that is a rather, how do you say, embarrassing question. So before I dare to put it on the slide here, I checked with a few sources, and it does not seem to be something that well, of course, I tried myself also, but it really looks like this is not easy. This is not an obvious. So anyway, maybe we'll stop here.